All right, we're live. We're live. Everyone, look up Lil Pump, the greatest musician, the voice of your guys' generation. Mine's maybe Vanilla Ice or something. I'm not sure. He could be the voice of my generation. Maybe. I guess Vanilla Ice is a little bit before my time, technically. He was in the Teenage Mutant Ninja Turtles movie, so.
Yeah.
Let's get it.
Like everywhere.
In that movie? I can't remember. I just know he was in there somewhere. I can't remember if it was a cameo, if he actually had like a large role. I think he's in the movie, like, and there's like a song.
Yeah, he did a couple songs.
Okay, anyway, let's look it up at the end of class. Okay, so let's look at 34. We're gonna do 34, and then we're gonna do 33. Bruh, why?
I said
Fine.
where's Winslow? Well, I guess they're
By the way, did anyone? I might have forgot to take attendance. Let me do that. But some food for thought, guys. On 32, I didn't mention this explicitly yesterday, but did anyone notice something about the numbers involved there? So when this was 20 and this was 5, remember the final calculation was, what did it end up being?
1.96.
Yeah, but just before we got the number, what two numbers were getting divided?
49 divided by 25.
49 divided by what? 25?
Oh. Give me a second like that.
Well, did you think about maybe like if you, think about that for a second while I do attendance. Think, where do those two numbers come from? Here, I'll write it like this, if this helps. It was 5 times 9.8 divided by 5 plus 20. Let's see, who's gone? Winslow's gone. Caleb's gone. Man, I'm so sad. Caleb missed. Caleb, if you're watching this, they said like Big Blue Moon on the announcements like 5 times. Or no, they didn't say Big Blue Moon. They said Blue Moon, and I think they also said the word big at some point. So technically, the phrase Big Blue Moon was in the announcements today, more than once. So it's very triggering, very upsetting to me. Okay. You guys see what I'm getting at here? Like, okay, how much force was exerted on the system? So let's say I think of this as being the system. That's the system. How much force is exerted on the system, the net force from outside the system? What I mean by that is, was there a force on this block that kind of went like this?
No.
Well, yeah, but that's kind of contained in the system.
Yeah.
We might call that an internal force, essentially, because it gets canceled out. And then, is there like a tension and a tension? Yeah, but that's still inside the system. The only thing from outside the system, the Earth is like, bruh, get over here. Earth is pulling down on the system with how many newtons of force? Well, 49 newtons. And then how much total mass is in the system? 25. So effectively, you can think of this in you gotta be careful when you do this kind of stuff, because a lot of times, if you try to apply this thought process too quickly, you might miss something. But anyway, in this particular case, you've got this being basically the net force, the net external force on the system, this being the total mass of the system, and giving your acceleration. You guys see what I'm talking about? Okay, so. You ever get like 10 messages in a row, and it's because people are like replying all to a huge email that no one should ever be replying all to?
Like in group chat, where someone's like, hey, practice tomorrow.
Thanks, coach.
Thanks, Coach.
Reply all. Thanks. I'll be there.
Thanks for letting us know, Coach. So glad we have practice tomorrow.
You get like 40 responses. Everyone, meeting for the entire company tomorrow. Okay, boss, thanks. Like, okay, you don't need to. If you got to reply, just reply to that one person. I guess you're like. Okay, so let's do the same process when it's. By the way, since this setup when it's M and M. So maybe we can just reason it out in our head. Then we're going to do it the complete way, but how much total force is going to be exerted on the system then from Earth? Mg, because yeah, this guy gets pulled down, but it gets canceled out of the table. So there's going to be mg force pulling it down. How much total mass is in the system? 2m. So what do you think the answer is going to be? Half of m, it would be mg divided by 2m, which is half a g. So 4.9 meters per second squared. Let's check to make sure that's correct. Doing it the good way, okay? So that's what I'm showing you there is that's sort of an intuitive way of kind of sort of guessing the answer ahead of time. And then you do it the thorough way and show, yes, that's actually true. So let's look at how much force is pulling this guy down. We just said it, mg. What's pushing him up? Tension, call that T. This right here is T, same T, but pointing in a different direction. And then there's going to be those two vectors that just cancel out, so I can kind of ignore those. Just let me confirm here, there's no friction on this problem, right?
No.
Okay, so we're going to throw friction in the next one we look at. So, okay, great. Let's write the F net equals MA for this guy. F net equals MA. Is everyone okay with why that says F net equals MA?
Mm-hmm.
Now let's write F net equals MA for this guy. F net equals MA.
Oh.
Everyone see what I did there?
Yeah.
There's a huge but kind of nuanced trick here, which is you have to consider this the positive direction. Now, what makes that a little confusing is if that is the positive direction, then this T is negative, but this T is positive. Did everyone understand that?
Mm-hmm.
Okay. So now, if you do an elimination, let's add these up. This plus this makes this. Oh, we get to use the banana theorem.
Yay.
1 MA plus 1 MA make 2 MA. Cancely time. Divide both sides by m, divide both sides by 2. There we go. Which, we can write it as a decimal, but this says a lot more, doesn't it? So that force, that mg force is basically getting split over double the mass, so you get half of g, half of what accelerates half as fast as it would have accelerated if you just dropped the block. Any questions?
So if you had just done mg divided by 2m, you would have gotten the same thing.
Yeah.
For 2.
Yeah, but that would not be generally considered like a valid approach. Like I was saying, it's a good sort of heuristic to be like, this is what I think the answer is going to be, but to actually show that this is the valid answer, you need to invoke Newton's second law, basically, which the other one's not really doing. What?
It's a Hoffman second law.
What? Okay. Big blue moon. All right. 34. Actually, no. Okay. I want you guys to figure out 34 in a row. We just did it with where they're the same M. What if they're not the same M? What if this one is M1 and this one's M2? Is the setup very different?
Probably not.
Well, no, it's not. The only difference is you're going to have I guess we can do this. The interesting part of this question is the very end of it, which is to answer what happens when M1 is much bigger than M2 or vice versa. Do you guys see where it says that?
Mhm.
So if I call this M1 and this M2, now what do I have to go and change? Do I have to change this? Yeah, this is now M2G. I can still call this tension just T, right? That still works. So when I go to write this guy's equation right here, I got to make it M2G minus T equals M2A. And when I write this guy's equation, it's got to be M1A. But that does change these next couple steps, right? Because now it's not one banana plus one banana anymore. It's different. It's actually, there's M2 apples plus M1 apples. Now you can think about it that way, I guess. Does that make sense? Maybe. I don't know, is that, because what are you going to get when you add up these two here? When you add up the left sides? M2G.
Mm-hmm.
What are you going to get when you add these up? You can say M2A plus M1A, right? Let's say I'd written it that way. Could I then factor out the A? Like that? Everyone understand that? Or I could have thought of it as if I have M2 many apples and I get M2 many more apples, I now have M1 plus M2 many apples, right? Does that make sense? Maybe?
No, not really.
No? Well, what if I had 3A plus 5A? I'd have 8A, right? Or what if I had 6A plus 4A? I'd have 10A.
Gotcha.
So I just, the number, the coefficient of A is just going to be the sum of those. But I maybe this makes more sense. This is fine. Add them up, factor out the A. Because ultimately I want to solve for A. So what do I do now? How do I solve for A? Divide this dude. Let's divide both sides by the quantity M1 plus M2. So I'm going to write it like this. Hope that's okay with y'all. Do you guys see how I did that?
Yeah.
Could this G live up here? Yeah, that's how fractions work. But this to me says a lot more. This is a lot clearer than writing M2G over M1 plus M2. They're mathematically equivalent. Okay, let's get to the more interesting part. Well, before we move on, does that all make sense? Are there any questions on any of these steps, like setting up the? Yes.
Why didn't you just cancel out the M2?
That'll make me sad, panda. That's not valid, right? So if you have, suppose you have very common mistake, right? Let's say I have 3 over 5 plus 3. I mean, that number's 3/8, right? So we know that this is 3/8. Can I just cancel out these 3's? No, that's not going to be. And the reason for that is you're probably thinking of like, suppose I had 3 divided by 5 times 3. That's a little different. If I had this is the same as 3/15, which when they say cancel out, what they're really talking about is I'm dividing the top and bottom of the fraction by 3 to get 1/5. So that's valid. That makes sense? But you can't, so what you'd be doing technically if you try to do something like this, what you're attempting to do is basically subtract 3 from the top and bottom, which wouldn't be a valid operation on a fraction. You can't, on a fraction you can multiply the top and bottom by the same value or divide the top and bottom by the same value, but you can't add or subtract the top and bottom by the same value. Does that all cool beans? Is that all perfectly cromulent? Anyway, let's answer this question. What happens when M1 is way, way bigger? They do this a lot in physics and engineering. They start asking these questions. What happens if this quantity is way bigger than this quantity? First of all, don't even look. What's your answer, Julia?
Acceleration is small.
Very good. Did you get that by mathematically or just kind of commonsensically?
Oh, well, I looked at the final answer before you covered it up.
This?
Yeah.
That's fine. I'm just wondering. So this answer, if you say this would imply a very small acceleration. Well, why? You can certainly look at this mathematically and say, look at this fraction. What if I had a huge number on bottom and a not very big number on top? Then my acceleration is going to be some small fraction of g, right? If you're confused, just make up numbers. Make M1 100 and make M2 1. And you'll find very quickly that you end up with a very tiny fraction of g. But how about just common sense wise? If this was a huge like refrigerator and this was like a penny, it's not gonna pull it hard enough to get it's not gonna move the refrigerator very fast, right? Even if it's perfectly frictionless. The acceleration is gonna happen very slowly. And then how about if M2 is way bigger than M1? Now this is where it gets interesting. Sometimes people will say this. People will go, oh, acceleration could be like 1,000,000. It goes to infinity. What would the acceleration be awfully close to if M2 was huge? Huh? Yes. It'd be very close to G. You guys see that? Now let's reverse it. Now this is the refrigerator, and this is the penny. Isn't the refrigerator pretty much just going to fall? I mean, the penny's not going to do much to hold it back. You know.
The refrigerator should just use its free will to not fall.
There you go. There's like a Futurama joke where someone's like, "Will this treatment fight the aging process?" And they go, "Well, in the same way that an infant might fight Muhammad Ali, yes." Just remind me of that. Okay, so anyway, so yeah, so this is so you can see that in the formula, right? If M2 was way bigger than M1, then imagine this was 99 divided by 1 plus 99. That's pretty much 1, right? So acceleration would be roughly equal to 1g. So, all right, cool beans. And I like this is one of the things I think is really cool about physics is getting this answer in sort of a rigorous way and then showing how the math agrees with what our common sense would think, which is I think kind of cool. Anyway, we got to do friction, right? If we have time, we'll look at the double both hanging. So, all right, I'm gonna read. I guess I'll read all the pictures. It's getting kind of cluttered up there. So 35 says, "What if we also throw some friction in there? Is that going to have a huge effect on the answers?" M1, M2, all right? But this time, there is friction. All right, guys, take a second. See if you can write the two formulas. You're going to write F net equals MA. Newton's second law. You're going to write that for this block and for this block. And I guess I'll give you a hint here. Does this guy know much about what's going on up here? No. He just knows that there's a string exerting tension on him. If you throw friction in up here, from his perspective, is it really any different from like maybe him just being heavier? Like, not really. So one of your equations will be the same. Definitely force diagram is a good place to start. And a hint if you're stuck is what direction does the friction force point on this? Does the friction push him this way or this way? It opposes where the motion's going to be. So there's going to be some friction force. And then how big is the friction force? So once you have your force diagram, this guy's force diagram is just the same. I should try to make these two tension arrows the same size. And this friction vector is probably going to be smaller than the tension, unless it's in static equilibrium. But it does say that it's seen sliding to the right. Did you get your equation, Cooper? Are you?
A little.
A little. F net equals ma, so write it to this guy. You know what the net force is, right?
I got one of them now.
Okay. And if you can solve it, great. Try to solve it. All right, you guys ready to check your answer? At least your equations? All right, someone give me this guy's F net equals ma equation. Who's got one? Say it again? Oh, T. Very good. So it's the T minus the mu m1g equals m1 times acceleration. And then this one is being very careful to treat on this guy, T is negative, whereas on this guy, T is positive. That's the big trick. Okay. All right, Julia, did you get the next step?
No, I just got this first.
Okay, that's fine. Elimination time. So when I add up this plus this, what do we get? Well, the T's cancel out, right?
Yeah.
Positive T, negative T. So I've got an M2G down here minus M1G. On the right-hand side, I got the M1A plus the M2A, which hopefully we know what's going to happen next with that, right? So let's do a little bit of factoring. I'm solving for A. So let me start with the right side. What can I do with these A's? Factor out the A. Also, in case it's not fairly obvious, like if you're solving for A, you only want there to be one A in the equation, right? The more A's, the harder your life's gonna be, right? Once you have just one A in there, you're like, okay, finally, I can just focus on that one variable and solve for it. Over here, can I do any factoring here to make it look nicer? Let's pull out the G. And if I factor the G, I've got M2 minus mu M1. Always be checking your answer here. That could be your new shirt, Henry. Always be checking your answer. Never mind. The mu is attached to the M1. Does that make sense that the mu would be attached to M1 since that's the guy that's experiencing the friction? Yes. So we're almost done, guys. Solve for A. By the way, this might look really confusing, but it's actually no different than like if you had, say, 7 times 5 equals A times 3. Is it really any different from that? A thing times a thing equals a thing times a thing. And the parentheses group those things together. So the answer to this would be 7 times 5 divided by 3. So our answer is G times, look at this beautiful expression. And then, I know what you guys are thinking. You're thinking, wait a second. Does that agree with the one we just did? 34? Are they compatible? What do you think?
Yeah.
So how can I check to see if this is compatible with the answer to 34? Very good. If you set mu to 0, that would be frictionless, right? If mu is 0, what do you get? The same formula that we had a minute ago. So it's the same. All right. You guys feeling okay about that?
Yes.
Okay. We're going to end with 36, the dreaded. This is kind of a famous type of question. They've been stumping people for years. The dreaded Atwood machine. There's been a meme for a long time of like where you're the student and you study and you finally understand the Atwood machine, like you finally like, okay, I understand it, and then on your test it's like, sorry. The test, they give you like this Atwood machine. You're like, no, I thought I knew how to do it. We're gonna keep them simple. It's just gonna be like simple Atwood machines. Except there is one we'll do this one together in class next week. 40 and 41 are pretty interesting. It's what if you have a self-supporting Atwood machine? Like how does that behave? It's pretty interesting. But so if you want a challenge, you can try to figure that out on your own. Okay, Atwood machine. This guy's 10 kilograms. This guy's 15 kilograms. Okay. So which way is the thing going to accelerate, obviously? Clockwise. So clockwise is the positive direction. Anti-clockwise is the negative direction. So it's the same principle as before. From this guy's perspective, the tension is negative, right? Julie's having a lid difficulty over there. There you go. Oh, she's got it. She's done it. Okay. From this guy's perspective, the tension is in the positive direction. Does that still make sense? Okay, so this guy, how much force is pulling him down? Always nice with numbers, right? So what's 15 times 9.8? Let me get there. 147 newtons. How much force is pulling him up? Do we know that yet?
98.
No. Here, I like that answer though. So here's why 98 is a reasonable answer, but it's not. It can't be the answer because 98 makes sense because this guy's experiencing 98 newtons down, isn't he? But if the tension in the string was 98, then wouldn't this guy be in equilibrium? He'd have 98, 98, so he would be accelerating. So that's a contradiction. So what you got to do is just call this t again, and same thing here. You got to call that t. We don't know what t is though yet. It's going to turn out that t is some number that there's, as far as I know, there's no like really obvious intuitive way to get t just directly from looking at 10 to the 15. It's not going to be obvious. So. Okay, let's write F net equals MA. Okay, how about this guy first? Write his formula. F net is that equals MA. Let's write this guy's formula. Again, being very careful with what's the positive direction. Tension points in the positive direction, so it's going to be T minus 98 equals MA. This is a good time for elimination. Now this, you should be happy right now, right? So you see that, you go, wait, I thought maybe this was going to be a lot harder, but it's actually not. It's just as easy as the other ones. So add these up. The t's cancel. 147 minus 98 is 49. 15 apples plus 10 apples is 25 apples. Yeah. Turns out that, you get that same. This is coincidence, happens to be the same result from before. Was it 9.6?
I think so. Yeah.
Now let's get the tension. How do you get the tension? Yep, plug it in. You pick whichever one. I'll pick the bottom one, seems easier. T minus 98 equals 10 times 1.96. And so, what do we get there? 172?
Yep, 117.6.
Too early for arithmetic. What was the tension we calculated on that other question where? What was the other question where we got the same acceleration?
32.
Notice on 32, it was a 20 versus a 5. It was quadruple the mass on the flat surface. And this one, they're very close. This is only 50% larger than this. But we got the same acceleration. It's kind of interesting to think about. And then what was the tension on 32? What did we get?
You got
39.2.
Right, so it's a good example of one where are there some similarities between the system in 32 and the system in 36? Yeah, same acceleration, but the acceleration was a result of a much different difference in masses, and then the tension is also much different in this question. So there you go. Kind of weird. Yeah, you see what I mean by the tension not being like intuitive?
Yeah.
Where's that coming from? All right, thanks for the 5 gifted.